I'm presenting fifth place solution, Team Famous. Famous is just an acronym for the first letters in our Kaggle nicknames. And I would like to first say thanks to the competition organizers and Kaggle for hosting such a challenging competition. It was a great, like, 2.5 week sprint for us, since we joined pretty late, and we worked really hard to end in 5th place. So in general, we can divide our pipeline in 3 main parts. First is to train our models on the initial data, then generate some additional data and train these models using this additional data, and repeat this process as many times as we can, and perform some optimization techniques on the final output to produce our final solution. So let's start with model architecture. You see, we considered some families for backbones, and it turns out that conformers and conformers worked the best for us, and we tried to experiment with some versions within the family. We tried large conformers, huge conformers, and so on, but I guess pretty small models in the end worked best for us. And I guess the key part here was to play with resolution. For example, we started to train our models using the resolution 72, and then we stop our training at some point when we see the convergence, and use this train checkpoint, these weights, to transfer it for further training on a larger resolution. And in the end, 144, 160, and 256 worked best for us, so we stick to it. And here are some additional hyperparameters that were used for our trainings. Cosine scheduler with 1 to the power of 10 minus 4. Constant scheduler work good. Also, there was a need for us to train for as many epochs as we can until we hit the convergence point. Large batch sizes also, standard mean average loss, and some tricks like touch compile, bfloat 16, pretty standard for this competition and other participants as well. So yeah, and the point is, using just competition data, it is possible to reach mean average 20 on the public leaderboard and private leaderboard as well. The next step for us, actually pretty crucial one, was to generate some additional data. On the slide, you can see a diagram with an explanation how we use this data. So we trained a model, then we generate some new data. We add to the additional, the initial data set, and we keep training. Then when we hit convergence, we stop our training, generate new data, extend it with the initial data, and resume training. And we did it a lot of times, like in the end, 7 or 8 iterations of creating new data. And this all was offline generation, so we didn't perform any on-fly augmentation. Instead, Actually, we did from one augmentation is flip augmentation, but the augmentations that we used were pretty time demanding, so we can't use it on fly. Yeah, so talking about the data generation pipeline, you see, actually, we can obviously create new additional data by solving for a problem. We can generate SACE images based on velocity images by restoring a simulator, and that allows us to use some data augmentation techniques for computer vision. For example, the most efficient one were cut mixes and mix-ups. We also implemented lens sites, as you can see on the screen. And so, yeah, we created a lot of additional data, like 8 or 10 times more than competition data set. And by that, I mean open FEI. Also, some more augmentation ideas. These are multiplication. You see the values that we had lied in the range between 150, 1,000 and 1,500 and 4,000 and 500. So we cropped them between these two values. And discrete families, by discrete, I mean any family besides styles. And these families can be just multiplied by some random values, but style families are different because we have to keep smoothness. And so we basically have to multiply it by a smooth function, for example, splines or some polynomials. Before transformations, we also remove the background gradient, and after that, we return it in the following way. Also, some rotations are pretty useful. And in the last, I guess, 2 or 3 days, we noticed that style A family looks like Berlin noise or with Gaussian blur. On the slide, you can actually see the example. So style A is really, at least from human perspective, looks like this noise. So we talked about the first part, the second part. Now the third part is post-optimization. It is also a very important part. And the high-level idea can be described as follows. So we have some ground truth SACE images, and by our models, we obtain predictions, velocity maps. And we use these velocity maps as a starting point for our optimization. We minimize the norm between ground truth and our prediction. And to do this, we implemented a differentiable version of Simulate, and we used just a simple gradient descent with mean average loss. And in the picture, you can actually see the image version of what I described. So we actually do this by many iterations, and we keep this process as long as we can. And by time, we obtain closer predictions. Yes, there are also some additional tricks to improve convergence. For example, we noticed that we can fight gradient vanishing by setting larger weights for later rows. But later rows, I mean, consider an image, and we can put an ordering on these rows. So by later rows, I mean just the lowest one. And also set larger unit rate to larger velocity pixels and adjacent pixels as well between the change of areas. And for flat families, predictions were pretty accurate, so we were able to exactly determine the respective edges, and we optimized we optimized it inside each row. And for sharp classes, discrete families, we applied TV-inspired regularization with parameter P equal to minus 0.6. Yeah, and to there's actually some more to prevent huge RAM usage during our optimization process. We set checkpoints after every 100 steps, and apply it torch compile to fuse some operation to actually speed up our calculations. And our final results are presented here. In the end, we used hill climbing family-wise to blend model predictions. Here I have to emphasize that we created classification models with high accuracy, 99.1. So we were able to distinguish classes pretty good. And most of mistakes of our model are between A and B version of the families. So yeah, by iterations in the last column, yeah, it's actually iterations in our post-optimization algorithm that we applied. That's all. Thanks.